The most dangerous moment of the Artemis II mission did not happen at liftoff. It has not happened yet. While the world was watching a rocket climb through Florida's evening sky, a geomagnetic storm was already active around the planet those 4 astronauts were leaving. A coronal mass ejection from the same solar flare that blacked out radio communications 5 days ago arrived at Earth during the launch window. Nobody interrupted the broadcast to mention it. Tonight, the translunar injection burn will fire, and when it does, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen will cross beyond the Van Allen belts, beyond the magnetosphere, beyond every layer of protection the Earth has ever offered our species for 8 days, while the sun remains loaded and aimed. Stay with me. What you're about to learn is the part of this story that the celebration was too loud to hear. If this has you hooked, subscribe to the Skylab and tell me what you think below. After a geomagnetic storm on launch night, an active solar region still aimed at the lunar trajectory, and a crew about to spend 8 days beyond the magnetosphere during solar maximum, are we asking enough hard questions about this mission? Or did the celebration drown them out? Let me know what you think. Now, let's get into it. Part 1. The real situation. They're already up there. Right now, as you watch this, 4 human beings are orbiting Earth at roughly 17,500 miles per hour, and almost nobody covering this mission has told you the most important part of what is happening. The celebration was real. The launch was extraordinary. But there is a layer to this story that got almost no airtime last night, and by the time I finish explaining it to you, the word celebration is going to feel like the wrong word entirely. Let me tell you what actually happened on April 1st, 2025. At 6:35 in the evening Eastern Time, NASA's Space Launch System lifted off from Kennedy Space Center, carrying 4 astronauts: Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. This was Artemis II, the first crewed mission beyond low Earth orbit since Apollo 17 in December of 1972. 53 years, more than half a century. And now, for the first time since the era of bell-bottoms and 8-track tapes, human beings are heading toward the moon. The crowd roared, social media exploded, news anchors used words like historic and milestone and triumph. And they were not wrong. It is all of those things. But here is the part that almost no one said out loud. They launched into a geomagnetic storm. A G1 geomagnetic storm alert was issued by NOAA's Space Weather Prediction Center, the SWPC, within hours of liftoff. This was not a coincidence. A coronal mass ejection, a CME, generated by the same X-class solar flare that blacked out radio communications on March 30th arrived at Earth during the launch window. The electron flux, measured at energies greater than 2 megaelectron volts, was registering at high, above 2,500 particle flux units. These are not my numbers. These are NOAA's numbers, verified, confirmed, publicly available, and yet somehow they did not make it into most of the coverage. Now you might be thinking, okay, a G1 storm, that's the lowest category on a 5-point scale. How scary can it really be? And that is exactly the right question to ask, because the storm itself is not the main story. The storm is a symptom. It is evidence of a solar environment that is already activated, already in motion, already delivering energy to the space around Earth, at the exact moment that 4 astronauts are preparing to leave the only magnetic shield our species has ever known. The mission has not yet entered its most dangerous phase. That happens tonight, when the translunar injection burn fires and commits this crew to a trajectory beyond the Van Allen belts, beyond the magnetosphere, into the open interplanetary space where the sun's behavior is no longer someone else's problem, it becomes their problem. Personally, biologically, in real time. This is not a launch story. I want to be very clear about that. The launch went beautifully. The rocket performed, the capsule is healthy, the crew is safe. What I am telling you is that the story most people think ended at liftoff is actually just beginning, and the most consequential chapter of that story involves a star 93 million miles away that has been unusually active, unusually complex, and is currently pointed directly at the path these 4 people are about to travel. So let's start there. Because what the sun has been doing this week is the context that makes everything else about this mission make sense, or rather, make you considerably more nervous. Part 2. The burn that changes everything. There is a moment coming in this mission that received almost no attention in the coverage, and it is arguably the most consequential single event in human spaceflight since the Apollo program ended. It is called the Translunar Injection Burn, the TLI, and it is not a technical detail. It is a threshold, a point of no return, a moment when these 4 astronauts stop being people who are technically in space and start being people who are genuinely, irreversibly on their own. Here is what the TLI actually means, stripped of the orbital mechanics jargon. Right now, in low Earth orbit, the crew is still inside Earth's magnetosphere, the magnetic bubble our planet generates from its molten iron core. The same bubble that has protected every living thing on this planet for billions of years. Inside that bubble, charged particles from the sun are deflected, bent away, redirected. The shield is not perfect, and astronauts on the International Space Station do receive elevated radiation compared to people on the ground, but they are still inside the system, still partially covered, still under the umbrella even if it's a leaky one. When the TLI burn fires, the Orion capsule will accelerate to a speed that breaks it free from Earth's gravitational dominance and commits it to a lunar trajectory. And as it climbs away from Earth, it will pass through the Van Allen belts, 2 concentric rings of trapped charged particles that act as a kind of outer filter layer for the magnetosphere. Crossing those belts is not comfortable. The radiation environment inside them is intense, and the crossing needs to happen relatively quickly. But the belts are not the destination. The destination is what's on the other side. Beyond the Van Allen belts, beyond the magnetosphere, the crew enters interplanetary space. And in interplanetary space there is no shield, there is no umbrella, there is no magnetic field bending dangerous particles away from their bodies. There is the sun, there is the galaxy, and there is the Orion capsule, and whatever that capsule can do to protect them on its own, with no external help from the planet they left behind. They will spend approximately 8 days in that environment, 8 days during which every proton, every high-energy particle, every burst of radiation the sun decides to emit will be travelling in their direction with nothing in between. No atmosphere, no magnetosphere, no planet, just distance and spacecraft walls. No human being has experienced this since December of 1972. The Apollo crews did it, yes, but they did it with 1970s technology, during a different phase of the solar cycle, and in missions that lasted days, not weeks. The longest any Apollo crew spent in translunar space was roughly 12 days, during Apollo 17, and even that mission had the advantage of launching during a quieter period of solar activity. Artemis II is launching at solar maximum, the peak, the moment of greatest solar energy output in an 11-year cycle, the moment when the sun is statistically most likely to do something dramatic. And here is the thing about the TLI burn that does not get discussed enough. Once it fires, the crew cannot simply turn around. There is no quick abort. There is no pulling over to the side of the road and waiting for conditions to improve. The trajectory physics of a lunar mission mean that once you commit to that burn, you are committed. You can execute a free return trajectory in an emergency, a path that uses the moon's gravity to slingshot you back toward Earth. But that takes time, days, and in deep space during an active solar event, days is a very long time. The launch was the part everybody watched. The TLI is the part that actually matters, and it is happening tonight, while the sun is already running warm. Part 3, the solar setup. Nobody is covering. Let me introduce you to active region 4405. You probably have not heard of it by name, but you have felt its effects. It is the solar active region, a cluster of magnetic complexity on the sun's surface that produced the X-1.4 class solar flare on March 30th. X-class flares are the most powerful category in the classification system, and that particular flare was powerful enough to cause high-frequency radio blackouts across multiple continents. That is the same flare whose associated CME arrived at Earth on April 1st, the day of the Artemis II launch. So region 4405 has already demonstrated that it is capable of producing events with measurable, real-world effects on Earth systems. That is not a theory, that is an established track record. And here is the part that should concern you. As of the launch date, region 4405 was still active, still magnetically complex, still classified as beta-gamma, which is solar physicist shorthand for a configuration where opposite magnetic polarities are tangled together in close proximity, exactly the kind of setup that produces flares. The SWPC's daily forecast showed a 75% probability of C-class flares, a 40% probability of M-class flares, and a 10% probability of another X-class flare every single day. 10% per day. That sounds manageable in isolation. One day, 10%, you might shrug and move on. But the Artemis II crew is going to spend 8 days beyond Earth's magnetic protection, and that 10% daily probability does not reset favourably. It accumulates. The cumulative probability of at least one X-class flare from region 4405 occurring during the mission's deep space window approaches 57%. Think about that number. The statistical likelihood that the most powerful class of solar flare fires at least once from a region already proven to produce them while these 4 astronauts are at their most exposed is higher than a coin flip. Not much higher, but higher. And it is not just region 4405 doing the work. Active region 4409 was also showing M-class flare potential. Region 4404 was contributing to a generally elevated background. The Sun, as of the launch date, was not presenting a single isolated threat. It was presenting a system of threats, multiple regions of magnetic complexity, each capable of producing events, all of them active during the same window. There is also a geometric dimension to this that matters enormously, and that almost no one explained during the coverage. It is not enough for a flare to be powerful. For a solar particle event to actually hit the crew, the source region needs to be positioned on the solar disk in a way that sends its output along the magnetic field lines that connect to the inner solar system, and specifically to the location of Orion. Region 4405 was, as of the launch, moving toward the center of the solar disk, the position that maximizes the probability of an Earth-directed and trajectory-directed event. The geometry was aligning at the same time as the mission window was opening. That is not a comfortable combination. Multiple CME candidates from April 1st eruptions were also under analysis at the time of launch. Not all of them were confirmed as Earth-directed, not all of them were confirmed as significant. But they were there, travelling outward through the solar system, and the crews of the missions that follow them into space do not have the luxury of waiting for the analysis to conclude before they have to act. The Sun is not quiet. It is conditionally unstable, and the condition is changing. Part 4. The timing problem. The timeline of this mission, laid out in chronological order, tells a story that the celebration coverage did not. On March 30th, active region 4405 fired an X1.4 class solar flare. That is the event that caused the radio blackouts. The flare produced a CME, a massive cloud of magnetized plasma ejected from the Sun's corona at hundreds of miles per second. On April 1st, that CME arrived at Earth. The ACE spacecraft, the Advanced Composition Explorer, which sits at a gravitational balance point between Earth and the Sun called the Lagrange. One point, about 900,000 miles from Earth, detected the solar wind spike, wind speeds climbing to around 500 kilometers per second. The magnetic field embedded in the CME was oriented southward, what solar physicists call a negative BZ orientation, which matters enormously because southward BZ is what allows the CME's magnetic field to connect with Earth's magnetic field and transfer energy efficiently. It is the condition that turns a CME from a near miss into a hit. Southward BZ is how geomagnetic storms happen. That is why the G1 storm was triggered. That is why the electron flux was elevated. That is the space weather environment that existed on the evening of April 1st, 2025, when the Space Launch System lit its engines and pushed 4 human beings toward the sky. And then there is the second driver, which is less dramatic but arguably more important for the mission's extended exposure window. A coronal hole high-speed stream was forecasted to arrive at Earth around April 2nd. Coronal holes are regions of the Sun's atmosphere where the magnetic field opens outward into space instead of looping back, allowing solar wind to escape at higher than average speeds. They are not as dramatic as CMEs. They do not produce the same explosive headlines, but they produce sustained elevated solar wind conditions that can extend a period of geomagnetic disturbance well beyond the initial CME impact. The SWPC forecast was calling for G1 conditions to remain active, with possible escalation to G2 through April 2nd and potentially beyond. That means the crew was not launching after a storm, or before a storm, or in between storms. They launched into a system of stacked disturbances, a CME impact already in progress, followed immediately by a high-speed stream that was designed by orbital mechanics to be ongoing exactly as they crossed the Van Allen belts and entered the unprotected space beyond. This is what solar physicists call a multi-driver environment. It is not one thing. It is 3 or 4 things arriving in sequence, each building on the energy state created by the previous one, extending the period of elevated activity across the exact window that matters most for this crew. They did not slip through a gap in the storm. They launched into a storm that was already scheduled to continue. And the important thing to understand is that everything I just described, the CME, the elevated electron flux, the coronal hole stream, the G1 alert, all of that was known. All of that was tracked. All of that was in the SWPC data in real time. The question is not whether NASA knew. Of course they knew. The question is what they decided to do with that knowledge. And that is a question we are going to come back to, because the answer is more complicated and more interesting than it might first appear. But first, let us talk about what happens to a human body when the shield disappears, because that is the part that the launch footage does not show you. Part 5. The invisible boundary. The magnetosphere is not a wall. I want to make sure that is clear, because the word shield tends to make people picture something solid, a dome of force, a hard edge where protected space ends and unprotected space begins. That is not how it works. The magnetosphere is dynamic. It breathes. It compresses on the side facing the sun and stretches out into a long tail on the night side. Its boundaries shift and flex in response to solar wind pressure. During quiet conditions, it extends roughly 60,000 kilometers toward the sun and millions of kilometers behind Earth. During a geomagnetic storm, the compressed sunward boundary can be pushed to as close as 20 to 25,000 kilometers from Earth's surface. It is alive in the way that weather systems are alive, responsive, variable, never quite the same from hour to hour. But for all its complexity, the magnetosphere performs one function that is, for our purposes here, absolute. It deflects charged particles, high-energy protons and electrons streaming from the sun, galactic cosmic rays arriving from across the galaxy. The magnetosphere bends them, captures them, shunts them around the planet. The Van Allen belts are the visible evidence of this process, zones where captured particles spiral along magnetic field lines, trapped in a kind of magnetic bottle that keeps them from reaching Earth's surface. The belts are dangerous to pass through, but they also demonstrate that the system is working. Those particles got caught. They did not reach you. Outside the magnetosphere, that process stops. There is no catching. There is no bending. Particles that would have been deflected around Earth now travel in straight lines through interplanetary space, and if the Orion capsule happens to be in the path of one of those particle streams, the capsule and everyone inside it absorbs the energy. The duration of 8 days matters here in a way that goes beyond simple arithmetic. Human beings evolved under near-zero radiation variability. We developed on a planet with a thick atmosphere, inside a magnetic bubble, with a sun whose output we were protected from at multiple layers simultaneously. Our biology has no defense mechanism for sustained high-energy particle bombardment, because in the entire evolutionary history of our species, we never needed one. The radiation environment in interplanetary space is not something the human body recognizes as danger and responds to. It is something the human body simply absorbs, cell by cell, DNA, strand by DNA strand, without any alarm system going off. Lunar surface data from the Chang'e 4 mission gives us a concrete reference point. The Chinese lander's radiation measurements clocked approximately 1,369 microsieverts per day on the lunar surface. For context, the average person on Earth receives roughly 3 millisieverts per year from all sources combined: natural background, medical imaging, everything. The lunar surface environment delivers that annual dose in roughly 2 days. The Artemis II crew will not be landing, but the interplanetary environment they will transit is comparable in its radiation profile. 8 days in that environment is not a minor inconvenience. It is a meaningful biological event, and its outcome depends significantly on whether the sun decides to add anything extra to the background noise. Part 6. Radiation is not one thing. When people think about radiation in space, they often imagine it as a single uniform hazard, some kind of invisible fog that gets thicker the further from Earth you go. The reality is considerably more complicated, and the distinction matters, because different types of radiation present different risks and respond differently to the countermeasures available inside Orion. The first type is galactic cosmic rays, GCRs. These are high-energy particles, often heavy ions that originate from outside our solar system. Supernovae, neutron stars, black hole accretion disks, these are the factories that accelerate particles to nearly the speed of light and send them streaming through interplanetary space in every direction, all the time, without pause. GCRs are, in a meaningful sense, omnidirectional background radiation that exists throughout the galaxy. You cannot predict when they arrive, because they are already arriving, constantly, from all directions simultaneously. They are also extraordinarily difficult to shield against. A high-energy ion nucleus travelling at a significant fraction of the speed of light does not politely stop at the wall of a spacecraft. It punches through, and as it does, it can actually generate secondary radiation, a spray of additional particles created by the collision with the shielding material itself. In some cases, more shielding is actually counterproductive for GCRs because you are just creating more secondary particles without stopping the primary one. The second type is solar particle events, SPEs. These are different in almost every important dimension. SPEs are dominated by protons rather than heavy ions. They are produced by specific events on the Sun, flares, CMEs, rather than arriving continuously from all directions. They arrive in bursts, with onset times of minutes to hours after the triggering event. And critically, they are far more responsive to shielding than GCRs. A sufficient mass of material, water, food supplies, equipment lockers, basically anything dense, can meaningfully attenuate an SPE. This is why the shelter protocol inside Orion exists. This is why the crew will know in advance exactly where to go and what to position around them. But here is the complication that sits at the centre of everything I am going to tell you. The mission risk is not dominated by the background levels of either GCRs or SPEs during normal solar conditions. It is dominated by the rare, extreme solar particle events, the events that fall at the high end of the SPE intensity distribution, the events that are not average, the ones that produce proton fluxes orders of magnitude above baseline. In a statistical model of deep space radiation risk, 90% of the probability mass might sit in a range that is manageable, uncomfortable but survivable with good shelter protocols. But that remaining 10%, the extreme tail, represents scenarios where the intensity of the event outpaces the protective capacity of the available countermeasures, and that 10%, rare as it is exactly why the solar environment at the moment of this mission's deep space transit matters so much. The question for Artemis II is not whether radiation exposure will occur. It will. The question is whether the Sun, during these 8 specific days, decides to contribute to the extreme end of the distribution. And the Sun, as we have already established, has been behaving in ways that move that probability in the wrong direction. Part 7. The 30-minute problem. Here is how a solar particle event unfolds from the perspective of someone inside the Orion capsule in real time. The flare occurs. At the moment of the flare, a pulse of X-rays and extreme ultraviolet radiation leaves the Sun travelling at the speed of light. That arrives at Earth, or at wherever Orion is, in roughly 8 minutes. It is the warning bell. Instruments detect it. Automated systems register the event. The alert chain begins. Then, depending on the geometry, the energy of the event, and the magnetic connectivity between the Sun and Orion's position, the first high-energy protons begin to arrive. These are the fastest, most energetic particles in the SPE, the ones that can arrive as quickly as 15 minutes after a major flare. The bulk of the proton flux typically peaks within 30 to 60 minutes of the triggering event, though for the largest events this peak can arrive faster, or in multiple waves, as successive particle populations travel along different magnetic pathways. That is the operational window. From flare detection to meaningful proton exposure, 15 minutes on the fast end, perhaps 30 to 60 minutes for the main particle population. During that window, the crew needs to receive the alert, assess the data, make a decision, move to the shelter location inside Orion, and position themselves with maximum shielding mass between their bodies and the incoming radiation. 15 to 30 minutes. With astronauts who are well trained and well prepared, who have rehearsed this sequence, that is achievable. But it is not comfortable. There is no margin for a false alarm that causes confusion, or a communication lag between Earth and the spacecraft, or a flare that originates from a position on the solar disk with limited advance warning visibility. And that last point introduces a genuine blind spot in the early warning system. The most dangerous category of solar particle events are those that produce the fastest particle arrival times, which tend to be associated with large, impulsive flares occurring on the western limb of the Sun, the limb that connects magnetically to Earth's position in the solar system. But if a flare occurs on the far side of the Sun, a region that Earth-based and Sun-Earth positioned instruments cannot see directly, there may be no warning at all, or warning that comes only from secondary signatures that take longer to interpret. Region 405, as of the launch, was positioned to produce Earth-directed events. But the Sun is a sphere, and it rotates. As the mission progresses, different active regions rotate into and out of the Earth-facing hemisphere. Some of those regions may not be visible until they are already capable of producing events. The warning system is reactive. It sees flares after they happen. It models CME trajectories with meaningful uncertainty ranges. It cannot tell you that a flare will occur tomorrow morning at a specific time. It can only tell you the conditions are favourable, and the conditions, right now, are very favourable for something to happen. The 30-minute problem is not a flaw in the mission design. It is a physical constraint of the solar physics involved, and the crew and mission controllers have done everything operationally possible to prepare for it. But preparation and elimination are different things, and it is worth being precise about which one is available here. Part 8. Orion's Shelter. How much does it really help? The Orion capsule is the most radiation-aware crewed spacecraft ever built. That is a true statement, and it is worth saying clearly before I tell you what it does not mean. NASA has thought carefully and seriously about the deep space radiation environment. The HERA sensors, the Hybrid Electronic Radiation Assessor, are mounted inside the cabin to measure the radiation environment in real time. Each crew member carries personal dosimeters. The capsule structure itself provides some baseline attenuation, and there is a designated shelter protocol that the crew will execute in the event of a solar particle event warning. The protocol works like this. The crew moves to a pre-designated area of the capsule near the heat shield at the back of the crew module and uses the available mass inside the vehicle to surround themselves as completely as possible. Water containers, food packages, equipment bags, anything with density gets positioned to create as much shielding mass between the crew and the incoming radiation as possible. It is, in essence, an improvised bunker inside a spacecraft that was not designed as a bunker. And it works, in the sense that it meaningfully reduces the dose compared to being in the worst position location inside the capsule during an event. Every centimetre of material between a proton and a DNA molecule is a centimetre that attenuates the energy of that interaction. But there are limits, and the limits are imposed by physics and mass budgets. A spacecraft that carries enough water and polyethylene to provide the shielding equivalent of Earth's atmosphere would never leave the ground. The shelter protocol reduces exposure, it does not eliminate it. For a moderate solar particle event, it may reduce the dose to a level that is within mission-acceptable parameters. For an extreme event, the kind of event that falls in the tail of the distribution I described earlier, the question of whether the available shielding mass is sufficient becomes genuinely open. The answer depends on the intensity of the event, its duration, the proton energy spectrum, the crew members' positioning, and the time they spend in shelter. The Apollo missions offer the most direct historical comparison, and the comparison is somewhat reassuring in some dimensions and sobering in others. The Apollo crews received radiation doses that were, on average, well within limits for their mission durations. Orion's shielding is improved over Apollo. The monitoring systems are orders of magnitude better. But the missions are also longer, and the solar environment during this mission is more active than during many of the Apollo lunar missions. And there is a harder question underneath all of this. The shelter protocol was designed for the most likely scenarios, moderate to significant SPEs, with warning times adequate to allow crew response. It was not designed for the tail event. The scenario where an extreme SPE arrives faster than modelled, with an intensity that exceeds the planning assumptions, while the crew is in a position inside the capsule that maximises their exposure, That scenario is not the design case, it is the margin. And the question of how much margin is enough is ultimately not a physics question, it is a risk tolerance question. And risk tolerance is a decision made by humans, not equations. Part 9. The August 1972 Near Miss. There is a date in the history of solar physics that does not get nearly enough attention in discussions of space exploration, and that date is August 4th, 1972. I want to tell you what happened, because it is the single most clarifying data point in any conversation about the radiation risks of deep space travel, and because it happened within the living memory of program managers and astronauts who work for NASA today. In August of 1972, the Sun produced one of the most powerful solar particle events ever recorded in the modern instrumental era. The proton flux was extraordinary. The event produced estimated doses that, for an unshielded human in interplanetary space, would have been in the range of thousands of rem, potentially lethal exposure. Satellite systems registered anomalies. Power grid fluctuations were recorded across North America. The event was, by any reasonable measure, one of the most extreme solar events of the 20th century. Here is what saved the Apollo program. Apollo 16 had returned to Earth in April. Apollo 17 would not launch until December. The August event occurred in the gap between them. No astronauts were in deep space. No human beings were beyond Earth's magnetic protection. The timing was not planned. It was not engineered. There was no decision made by NASA that protected those crews from that event. The protection was pure coincidence. The Sun fired its most extreme recorded shot at the inner solar system, and there was nobody there to be hit. In the 53 years since that event, no human being has been in a position to be affected by an August 1972 scale event. Because in those 53 years, no human being has been beyond Earth's magnetic protection, until now. That is not to say that Artemis II will encounter an August 1972 event. The probability of any specific mission encountering an event of that extreme magnitude during its window is low, but the probability is not zero, and it has never been properly quantified, and the mission is launching during solar maximum, the period of the 11-year solar cycle, when the probability of extreme events is at its highest. The August 1972 event did not announce itself in advance. The forecast in the days before it did not predict its full intensity. It happened at its own pace, on its own schedule, and the only reason it did not define the Apollo program's legacy in a much darker way is that nobody happened to be there. Somebody is there now, 4 somebodies, and the Sun is running hotter than it has in a decade. Part 10. NASA knew the conditions. Let me be direct about something, because this is the part of the story that is most likely to be misread if I do not frame it carefully. NASA knew about the CME. They knew about the elevated electron flux. They knew about active region 4405 and its magnetic complexity and its established record of producing X-class flares. They knew the coronal hole high-speed stream was incoming. They knew the SWPC was forecasting G1 storm conditions, possibly escalating to G2 around the launch window. All of this information was publicly available, was being tracked in real time by NOAA, and was almost certainly being fed to mission planners through dedicated space weather support channels that are more detailed than anything available to the public. I want to say that again clearly, because it is important. The conditions I have been describing to you for the past 20 minutes were not hidden. They were not unknown. They were not discovered after the fact. The people who made the decision to launch Artemis II on April 1st, 2025, made that decision with full awareness of the solar weather environment into which they were sending this crew. That is not a criticism. Or at least it is not necessarily a criticism. It is a fact, and it is a fact that changes the character of the story. This was not a case of an unexpected solar event catching a mission by surprise. This was a case of a mission launching into a known, monitored, quantified, elevated risk environment, following a deliberate decision by the people responsible for the mission. Which means the next question is, what was their reasoning? What calculation did they run? What trade-offs did they consider? Because the answer to that question tells you something important about how we as a species approach the risks of pushing beyond the boundaries we have always lived within. Part 11. The internal risk calculation. The logic that led to the launch decision, as best as it can be reconstructed from what is publicly known about how NASA approaches these decisions, runs roughly as follows. Solar maximum is not optional. The 11-year cycle of solar activity does not pause for program schedules. Artemis II was always going to launch near solar maximum because the program timeline demanded it, and the solar cycle does not take requests. If the condition for launch approval were no elevated solar activity, there would be no launch window for approximately 4 years. That is not operationally acceptable. The Orion capsule was designed for this environment. The radiation monitoring, the shelter protocols, the HERA sensors, the dosimeters, all of it exists precisely because this mission was always planned to transit the deep space radiation environment during solar maximum. The engineering confidence is not that the environment will be benign, it is that the vehicle and crew can manage the environment as designed. The program economics are real. Each launch of the Space Launch System costs approximately $4 billion. A delay is not free. It is not just the cost of another launch attempt. It is the cascading delay of every subsequent mission in the program, Artemis III, the first crewed lunar landing attempt, which depends on Artemis II completing successfully. Every month of delay to Artemis II is a month of delay to the first woman and first person of colour to walk on the lunar surface. And there is a geopolitical dimension that rarely gets discussed openly, but almost certainly factors into program decisions at the level of priority and timeline. China has stated publicly that it intends to land human beings on the moon by 2030. The Artemis program is, among other things, an assertion of American leadership in space exploration, at a moment when that leadership is genuinely contested. A delay is not just a delay on a spreadsheet. It is a point in a competition with a geopolitical adversary. So when you place the elevated solar activity in one pan of the balance, and all of those factors in the other pan, the calculus that produced the launch decision begins to make a kind of institutional logic. It is not reckless. It is not incompetent. It is a deliberate rational risk acceptance, accepting a quantified increase in mission risk in exchange for maintaining program momentum. The question is whether that trade was the right one, and on that question not everyone agrees. Part 12. The counter-argument. There is a perspective within the solar physics and space medicine research community, not unanimous, not universal, but present, that looks at the conditions of this launch and lands in a different place. The argument stated directly is this: the 10% daily probability of an X-class flare from region 4405, accumulated over 8 days of deep space transit, produces a mission duration probability of an extreme solar event that is meaningfully higher than the baseline risk assumed in program planning. The active solar environment does not just add a constant increment of background radiation. It increases the probability of the tail events, the extreme SPEs that sit outside the routine design cases and within the territory where the available shielding may not be adequate. When you are operating near the tail of a risk distribution, small changes in the conditions can produce disproportionately large changes in the expected outcome. The counter-argument to the launch is not that the risk is certainly too high. It is that the elevated conditions shifted the risk distribution in a direction that, for a mission with these stakes, 4 human lives, a program that humanity has not attempted in more than 50 years, warranted a harder look at whether a delay of days or weeks to allow region 4405 to rotate off the Earth-facing disk would have meaningfully reduced the probability of an extreme event during the critical transit window. But here is the nuance that makes this genuinely difficult. There is no safe window during solar maximum. Region 4405 rotates off the Earth-facing disk, but other regions rotate on. The Sun does not offer a quiet month during its peak activity phase. A delay of 2 weeks gets you past this specific active region, but deposits you in a different solar environment that may be equally or more complex. There is no objectively correct answer. There is only a choice between different configurations of uncertainty and the question of how much weight to give to the program factors versus the incremental biological risk to the crew. That is a legitimate disagreement among reasonable people, and I think it deserves more public attention than it has received. Because these 4 astronauts are not only the crew of Artemis II, they are the data point on which the risk models for every subsequent crewed deep space mission will be calibrated. Whatever happens during this transit, good or bad, becomes the baseline for what comes next. Part 13. The point of no return. Within hours of this conversation, that translunar injection burn will fire, and when it does, the nature of this mission will change in a way that is worth sitting with for a moment. Before the TLI burn, the crew is in Earth orbit. The distance between Orion and Earth's surface is measured in hundreds of miles. A medical emergency, a spacecraft anomaly, an unexpected solar event. These things are bad, but they are bad in a context where options exist. Emergency return trajectories from low Earth orbit can be executed in hours. The crew is close enough to Earth that ground stations have constant communication contact. The problem space is large, but it is a problem space that human beings have been working in continuously since 1961. We know how to manage emergencies in Earth orbit. After the TLI burn, the crew is in a different category of situation. The distance from Earth begins to grow continuously. Thousands, then tens of thousands, then hundreds of thousands of miles. Communication with mission control continues, but the psychological reality of that communication changes. They are not close. They cannot be retrieved quickly. The resources available to them are the resources in that capsule, and the decisions available to them are the decisions they can execute with what they have. Free return trajectories exist for lunar missions, paths that use the moon's gravitational influence to bend the spacecraft back toward Earth without requiring a propulsive burn. The Apollo program used this architecture, and Artemis II incorporates a similar capability. But a free return trajectory is not a fast rescue. It takes days, and in the context of a significant solar particle event, days is the relevant timescale for continued exposure if the shelter protocol is insufficient. Once the burn fires, these 4 people are committed, not in a dramatic theatrical sense, in a precise physical orbital mechanics sense. They are committed to a trajectory that carries them beyond the boundary that has separated every human being in history from the unshielded radiation environment of interplanetary space. They are committed to spending 8 days in a region of the solar system where the sun is the only relevant weather system, and the sun is actively producing conditions that required a NOAA storm alert on the day they launched. There is something profound about that, separate from any risk calculation. Humans spend a great deal of time building systems to manage uncertainty, to reduce it, contain it, predict it, engineer around it. But at the far end of every one of those systems, there is a residual uncertainty that cannot be designed away. The Artemis II crew is, right now, in the vicinity of that residual, and they went there knowingly, voluntarily, on behalf of a species that needed someone to go. Part 14, Region 4, 405 as a system. To understand why active region 4405 is worth treating as more than a single data point, you need to understand what makes a solar active region dangerous, not just in the moment, but as a sustained system over time. Active regions on the Sun are concentrations of intense magnetic field that emerge through the solar surface from below. They appear as groups of sunspots, darker, cooler patches that are cooler only relative to the surrounding solar surface, which is itself roughly 5,500 degrees Celsius. The magnetic fields in active regions are not orderly. They are tangled, sheared, stressed. When opposite magnetic polarities are forced close together, when a north magnetic region and a south magnetic region are pushed into adjacency by the constant churning of the solar surface, the configuration becomes what physicists call non-potential. Energy is stored in the magnetic field, and when that stored energy is suddenly released through a process called magnetic reconnection, where field lines of opposite polarity snap apart and reconnect in a lower energy configuration, the release is violent and rapid. That is a flare. That is a CME region 4405 was classified as beta-gamma. In the solar physics magnetic classification system, beta describes a region where opposite polarities are present within the same sunspot group, sharing a common penumbra. Gamma describes configurations where the opposite polarity regions are fully mixed, thoroughly entangled rather than simply adjacent. Beta-gamma is therefore a region with significant stored magnetic energy and a geometry that promotes rapid energy release. It is not the most complex classification available. That would be beta-gamma delta, where the opposite polarity umbrae are within the same penumbral boundary. But it is firmly in the category of regions that solar physicists watch closely and forecast with elevated concern. The region had demonstrated its capabilities. The X1.4 flare on March 30th was not a maximum output event for a region of this complexity. It was a moderate-large event. Regions of this classification are capable of producing X2, X3, even X5 class events. each of which would represent a proportionally larger proton flux and a proportionally greater SPE risk for the crew. And as of the launch date, the region was not declining. It was not dissipating. It was moving toward the center of the solar disk, the position that maximizes Earth-directed output, and its magnetic configuration retained the complexity that had produced the March 30th event. This is not a region that fired once and exhausted itself. It is a region that remains capable, and it will remain in an Earth-facing trajectory-directed position for a significant portion of the Artemis II deep space transit window. Part 15. Probability versus reality. There is a specific cognitive error that people make when processing low daily probabilities, and it is one of the most important things I can help you correct before you think about this mission's radiation risk. 10% per day sounds small, 1 in 10. You probably would not avoid an activity on any given day if someone told you it had a 10% chance of going wrong. But the relevant number is not the daily probability. The relevant number is the cumulative probability over the mission duration, the probability that at least one event occurs across all the days of potential exposure. The math is straightforward. If the probability of an X-class flare on any given day is 10%, the probability of no X-class flare on that day is 90%. For 8 consecutive days, the probability of 0 X-class flares across the entire window is 0.9 multiplied by itself 8 times, roughly 43%, which means the probability of at least one X-class flare during the 8-day deep space transit window is approximately 57%. 57%, more likely than not. And that is the cumulative probability from a single active region, region 4405, with other active regions on the solar disk contributing additional independent probability. The combined probability of at least one X-class event from any source during the mission window is higher than 57%. Not dramatically higher, but higher. Here is the additional layer. Not every X-class flare produces a dangerous solar particle event. The proton flux depends on the particle acceleration efficiency, the magnetic connectivity to Orion's position, and several other factors that vary event by event. An X-class flare that is not well connected to the inner solar system trajectory may produce a large X-ray pulse and minimal SPE. Conversely, a moderate M-class flare from a well-connected region can produce a more dangerous SPE than a larger flare from a poorly connected region. The X-class probability is a proxy for risk, not a perfect predictor. But what it tells you is that the probability of conditions arising that could threaten crew safety is not negligible. It is not a tail probability so small you can dismiss it. It is a meaningful fraction of the probability space. And the crew, once they cross the Van Allen belts, will be living inside that probability space, making real-time decisions about shelter and exposure based on data that is arriving with 15 to 30 minutes of advance notice. That is the situation. Not theoretical, not hypothetical, current. Part 16. What if it fires again? Let me walk you through the scenario. Not the worst case, not a disaster movie. Just the sequence of events that would unfold if region 4405 produces another significant flare while the Artemis II crew is in deep space transit, because understanding the sequence is the only way to properly evaluate the system's capacity to respond. The flare occurs. X-ray emission spikes. A CE at the Lagrange 1 point detects the initial X-ray pulse within 8 minutes of the flare. NOAA's automated systems register the event and begin the alert cascade. Mission Control receives the notification. Ground-based coronagraphs and solar observatories begin analysing the post-flare imagery for evidence of a CME. The determination of CME characteristics, speed, direction, angular width, the likely proton energy spectrum takes time. Not hours, but minutes to tens of minutes. The models that predict CME propagation and whether it will produce a significant SPE at Orion's position are good, but they are probabilistic. They provide ranges, not certainties. A fast, Earth-directed CME with a strong associated proton event will be detected in the data. The question is how quickly the detection translates into a clear, actionable signal for the crew. Mission Control issues a shelter advisory. The crew moves to their designated shelter position. This is the rehearsed sequence, and for astronauts of this caliber, it executes quickly. They are inside a capsule that is not large. The shelter position is known, the procedure is drilled, then they wait. The proton flux builds, slowly at first, then rapidly as the bulk of the SPE particles arrive. The HERA sensors inside Orion provide real-time dose rate data. The crew knows what they are receiving per unit time. The question of how long they remain in shelter depends on how long the proton flux remains elevated, which for a significant SPE can be hours, and for a large event can extend across multiple days as successive particle populations arrive along different magnetic pathways. The outcome range is genuinely wide. A moderate SPE handled with good shelter protocol and adequate advance warning produces elevated but mission-acceptable doses. A large, fast SPE that arrives with minimum warning time and produces a proton flux at the high end of the historical distribution produces outcomes that are harder to characterize in advance. The shielding is finite. The event duration is uncertain. The crew's cumulative dose across the mission, GCR background plus any SPE contribution, determines the biological outcome. Not all X-class flares produce dangerous SPEs, as I said. Direction matters as much as intensity. But Region 4-405 has already demonstrated Earth connectivity. The geometry is already in the dangerous category. Another eruption from the same region, during the same deep space transit window, would be connected. The pieces are in place. The only missing variable is whether the Sun pulls the trigger. Part 17. Detection Limits. The Solar Monitoring Network is extraordinary by any historical standard. SOHO stereo. A CE, DS, CO, VR, the SDO, ground-based observatories on every continent. The Sun is watched constantly, from multiple angles, across multiple wavelengths, with instrumentation that would have seemed like science fiction to the Apollo-era flight surgeons who were managing this same fundamental risk in 1972 with a fraction of the data. But monitoring is not prediction, and the detection system has limits that matter for this mission. The most important limit is the far side of the Sun. Earth-based and Lagrange 1 positioned instruments see the Earth-facing solar hemisphere with excellent resolution. But the Sun rotates, one full rotation every approximately 25 to 27 days, and active regions that are currently on the far side of the Sun are not directly visible to most monitoring assets. Stereo provides some far-side coverage, but not at the resolution or cadence of the primary monitoring instruments. A large active region rotating onto the Earth-facing disk could go from invisible to fully capable of producing events within days. The warning time for a far-side surprise is short. There is also a latency dimension to the CME modelling. When a CME is detected by ACE at the Lagrange 1 point, 900,000 miles from Earth, the lead time before it reaches Earth is typically 15 to 60 minutes. That is the window in which the shelter advisory must be issued, and the crew must respond. For Orion at lunar distance, roughly 239,000 miles from Earth, but in a different geometric position relative to the Lagrange 1 point, the timing calculation is more complex. The CME travel time to Orion's position depends on the CME's trajectory and speed, and the models that predict this have uncertainty, ranges that can span tens of minutes. And the models themselves, the physics-based predictions of CME trajectory, speed, and particle acceleration efficiency, are good but not perfect. They predict a range of outcomes. They have been validated against historical events. But the extreme events, the tail of the distribution, are by definition rare, and rare events are the hardest to model accurately because there are the fewest data points to constrain the models. The system works well for common events. For the uncommon ones, the ones that matter most, the uncertainty is larger, and the margin between the model's central prediction and the actual outcome can be substantial. This is not a criticism of the monitoring infrastructure. It is a physical reality of predicting the behavior of a complex, turbulent, magnetically active star across 900,000 miles of space. The system reduces risk. It does not eliminate uncertainty. And for 4 people in a capsule beyond the magnetosphere, that residual uncertainty is personal. Part 18. The Unspoken Truth. Everything I have described to you, the monitoring systems, the shelter protocols, the HERA sensors, the dosimeters, the forecast models, the engineering margins built into Orion's design, all of it represents a genuine, serious, technically sophisticated attempt to manage a fundamentally unmanageable environment. And I mean that in the most respectful possible sense. The people who built these systems are not naive. They understand that they cannot eliminate the risk. They have spent careers trying to reduce it to a level that a reasonable human being, fully informed, might choose to accept in exchange for the objective of reaching the moon. That is not a small thing. That is decades of physics, engineering, medicine, and institutional will compressed into a capsule the size of a large living room, sent beyond the edge of everything we have ever called safe. But there is a truth that sits underneath every press release, every mission briefing, every post-launch celebration, and it does not appear in the official documentation, not because anyone is hiding it, but because it is the kind of truth that does not fit cleanly into a risk matrix or a program schedule. The safety of the Artemis II crew in deep space depends, more than any monitoring system, more than any shelter protocol, more than any sensor array, on the Sun not doing anything unusually dramatic during 8 specific days in April of 2025. That is the foundation on which everything else rests. The technology helps, the training helps, the protocols help, the dosimeters help. But they all operate as multipliers on a baseline condition, the condition that the solar environment during those 8 days stays within the range that the countermeasures were designed to handle. Step outside that range and the multipliers are still working. But the thing they are multiplying has changed in a way that the engineering did not fully anticipate. This is not a criticism of the engineering, it is a description of the physics. Deep space is not a controlled environment. It cannot be made into one, not now, not with any technology currently available or on the near-term horizon. You cannot install a magnetosphere inside a spacecraft. You cannot carry enough shielding mass to replicate Earth's atmospheric protection without building something that could never leave the ground. The radiation risk in interplanetary space during solar maximum is irreducible below a floor that is set not by what engineers decide, but by what stars do. And stars, as a category of object, are spectacularly indifferent to human program timelines. The Sun will do what the Sun will do. It has been doing it for 4.6 billion years without consulting anyone. The 11-year activity cycle peaks when the physics of the solar dynamo says it peaks. The active regions emerge, evolve, and erupt according to magnetic field dynamics that we can model with increasing sophistication, but cannot influence in any direction. Region 4405 does not know that Orion is in its field of view. It does not know about the shelter protocol, or the 30-minute warning window, or the cumulative probability calculations that solar physicists were running in the days before launch. It is a concentration of tangled magnetic field on the surface of a star, and it will do what tangled magnetic fields on stars do, on its own schedule for its own reasons, without regard for the 4 human beings currently travelling in its general direction. And the crew, inside their capsule, beyond the belts, beyond the magnetosphere, will absorb what the monitoring and shelter systems cannot prevent. That sentence is worth sitting with, not in a fatalistic way, not as a statement of despair, but as an honest accounting of what is true. There is a fraction of the radiation environment in translunar space that will reach the crew, regardless of what they do, where they position themselves, how quickly they respond to alerts, how well designed the HERA sensors are. The background GCR flux is continuous and omnidirectional and passes through spacecraft walls with an indifference that mirrors the Sun's own. The question is not whether the crew will receive radiation. They will. The question is whether the dose they receive falls within the range that the human body, monitored and supported by modern medicine, can absorb without lasting consequence. That is the truth that the celebration coverage did not include. And I want to be careful here, because I am not saying the coverage was wrong to celebrate. The launch was genuinely extraordinary. The achievement was real. The engineering that put 4 people on top of that rocket and sent them safely into orbit is a monument to human capability, and it deserves the recognition it received. The people at Kennedy Space Center who watched that vehicle climb into the Florida evening sky had earned every moment of that feeling. I'm not here to take it away from them, but celebration and understanding are not the same thing. And a civilization that only does one of them, in relation to its most significant endeavours, is a civilization that is not fully reckoning with what it is actually doing. The Apollo program was celebrated too, and it should have been. It was also a program in which 3 astronauts died in a launch pad fire, in which Apollo 13 nearly became a catastrophe, in which the August 1972 solar event passed through the exact orbital region that 12 men had walked through and would walk through again, and the only reason it did not define the program's legacy in a darker way was timing. Not planning, not engineering, timing. The Sun fired its most powerful recorded shot at the inner solar system in 1972 and missed the crew because the crew happened not to be there. That is not a risk management success story. That is a close call that never got close enough to be recognised as one. The argument for going, let me be clear about this, is real and serious and not to be dismissed. The exploration imperative that drives programs like Artemis is not vanity. It is not bureaucratic momentum. It is the expression of something genuine in the human character, the need to go further, to know more, to extend the boundary of where our kind has been. The scientific return from crewed lunar missions is substantial. The technical knowledge gained from putting humans in deep space and bringing them back safely will be foundational for every mission that follows to the moon and beyond. And the human statement of what the species can do, the declaration that we are still capable of this, that we have not retreated into safety and comfort at the cost of ambition, that statement has a value that does not appear on any budget spreadsheet but is nonetheless real. But understanding what is being asked of this crew and what is being trusted to hold, not just the engineering, but the behaviour of a star, the timing of a magnetic eruption, the geometry of an active region rotating across the solar disk during an 8-day window, that understanding is part of what it means to take this mission seriously, to actually honour what these 4 people are doing rather than simply applauding it. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen, they know the unspoken truth. They have read the same solar physics literature. They have sat through the same radiation risk briefings. They have looked at the same SWPC forecasts that showed the G1 storm active on their launch night and the cumulative X-class probability sitting above 50% for their transit window. They know what they are flying into. They chose to fly into it anyway. That choice deserves more than celebration. It deserves comprehension. And right now, as the translunar injection burn either approaches or has already fired, the Sun is still active. Region 4405 is still on the disk. The daily probability of an X-class event is still approximately 10%, accumulating with every day that passes, adding to a cumulative risk figure that is already above the threshold most people would consider negligible. The margin between mission success and something much harder to talk about is, at least in part, a function of what happens in the next 8 days on the surface of a star that does not know we are watching it. That does not know we are out there. That is simply, as it has always been, doing what stars do. We sent 4 people into that, and we are trusting the universe to be, for just these 8 days, a little less than its full self. Part 19. The 12-hour convergence. On the night of April 1st, 2025, while 4 astronauts were ascending into orbit and the Sun was delivering a geomagnetic storm to the planet they were leaving behind, the Earth itself was not still. In a 12-hour window centered roughly on the launch, a series of events occurred that, taken individually, would each have been notable. Taken together, they produced a picture of a planet that was, in its own way, as unsettled as the space environment its crew was entering. And if you are the kind of person who pays attention to convergences, not because you believe in cosmic conspiracy, but because convergences sometimes tell you something about the state of a system, this particular 12-hour window is worth examining carefully before we return to the crew, because what was happening on Earth that night provides the most clarifying possible contrast to what those 4 people were heading into. A magnitude 7.4 earthquake struck the coast of Indonesia. The seismic event was significant enough to generate tsunami waves that reached populated coastlines, triggering evacuation orders and emergency response across multiple island communities. Thousands of people were displaced from coastal zones. Emergency sirens sounded across regions where the memory of the 2004 Indian Ocean tsunami is not historical knowledge, but lived experience, passed down through families who lost members to the water. The earthquake itself lasted seconds. Its consequences extended across hours, and for the communities affected, across much longer than that. Simultaneously, in the central and eastern United States, a severe weather outbreak was underway that by any metric was a significant meteorological event. The National Weather Service issued 469 separate alerts in a single day: tornado warnings, severe thunderstorm warnings, flash flood emergencies, high wind advisories stretching from the Gulf Coast to the Great Lakes. Tornadoes touched down across multiple states. Damaging winds flattened structures. Flash flooding turned roads into rivers and trapped people in vehicles and low-lying areas. The full catalogue of convective violence that the American spring is capable of producing was, on that particular night, producing it. Meteorologists were running on reduced sleep. Emergency managers were coordinating across state lines. Local news broadcasts were cycling through warning maps that barely had time to update before the next cell crossed the county boundary. And above all of it, invisible to every camera and every weather radar, the geomagnetic storm generated by the CME impact was inducing currents in power grid infrastructure across the high-latitude regions of North America and Europe. Not catastrophically, a G1 storm is the lowest category, and modern grid operators have protocols for geomagnetic disturbance events, but measurably. The storm was doing what geomagnetic storms do, quietly stressing systems that most people do not think about until they stop working, while the broadcast coverage focused entirely on the rocket climbing through the Florida sky. None of these events are statistically unique in isolation. I want to be careful about that, because the temptation when events converge in time is to assign them a meaning that the individual events do not necessarily carry. Indonesia is one of the most seismically active regions on Earth. It sits on the Pacific Ring of Fire, where tectonic plate boundaries converge in configurations that make significant earthquakes not a question of if, but of when. A magnitude 7.4 event in that region, while serious and damaging, is not geologically anomalous. It is a manifestation of a geological reality that has existed for millions of years and will continue long after the Artemis program concludes. American spring weather produces severe outbreak days with regularity. April is peak tornado season across the central United States. 469 NWS alerts in a day is extraordinary, but it's not without precedent in the meteorological record. The individual events, examined separately, fit within the known behaviour envelope of an active, dynamic planet. But the convergence of timing is, at minimum, striking, all of it unfolding within hours of a launch that itself coincided with an active geomagnetic storm creates a tableau that invites reflection, even if it resists simple interpretation. The planet was not quiet on the night its crew left. It was generating earthquakes and tornadoes and tsunami warnings and geomagnetic disturbances simultaneously, as if running through a checklist of the things it is capable of, while 4 of its inhabitants strapped into a capsule and chose to leave. I want to be precise here, because precision matters in both directions, and this is the kind of topic where imprecision can pull a story in directions that the evidence does not support. There is no established causal mechanism in mainstream geophysical science that links geomagnetic storms to the triggering of earthquakes on the timescales involved in this convergence. The Earth's crust is not a system that responds to magnetic field perturbations of the magnitude produced by a G1 storm in ways that would advance or trigger a tectonic rupture. The physical coupling between the ionosphere and the lithosphere, at the scales relevant here, is not understood to operate in that direction with that speed. Saying the CME caused the earthquake is not supported by the evidence, and I am not saying it. The earthquake happened because tectonic plates moved along a fault boundary that had been accumulating stress for years, possibly decades, and reached a threshold on April 1st, 2025, for reasons entirely internal to the geological system. The geomagnetic storm happened because a CME arrived at Earth, carrying a southward-oriented magnetic field that connected efficiently with Earth's own magnetosphere and transferred energy into it. These are separate physical systems, and their simultaneity on this particular night is, by the most rigorous available assessment, a coincidence. But here is what the coincidence illuminates, regardless of its cause. The 12-hour window produced a concentration of geophysical events that forms a meaningful backdrop to the story of 4 humans leaving an unsettled planet for an even less protected environment. While the Earth was registering seismic shocks and tornado warnings and flood emergencies and grid disturbances, those 4 people were ascending into a radiation environment that made everything happening on the surface look, in terms of the personal risk to the individuals involved, relatively manageable, not trivial. The people affected by the earthquake and the tornadoes and the flooding were in genuine danger, and some of them were hurt, and none of their experience should be minimized. but manageable in the specific sense that the word means when applied to risk, containable within a system that has resources, redundancies, and the accumulated knowledge of a species that has been surviving these events for as long as it has existed. The contrast is the point, and it is worth dwelling on it for a moment before we move forward. The chaos of the launch night was earthly chaos, frightening, damaging, real, consequential, the kind of chaos that produces headlines and emergency declarations and congressional disaster relief requests. But it was occurring within a planetary system equipped with an atmosphere that limits radiation exposure, a biosphere that has co-evolved with the planet's geological and meteorological violence, emergency services with equipment and training and communication infrastructure, rescue operations that can reach affected areas within hours, hospitals with the capacity to treat injuries, and the entire collective scaffolding of a civilization that has spent millennia learning, at significant cost, how to survive the things its own planet does to it. What the Artemis II crew was heading into had none of that scaffolding. No atmosphere, no rescue services, no hospitals within reach, no planetary magnetic field to soften the solar wind, no accumulated civilizational knowledge about how to survive the thing they were entering, because no civilization has ever existed in that environment long enough to develop survival knowledge about it. The Apollo program gave us 12 days of crude deep space experience spread across 6 missions, all of them completed more than 50 years ago. That is the entire baseline. That is everything we know from direct human experience about what it takes to survive beyond the magnetosphere. 12 days, 6 missions, 50 years ago. The Earth on April 1st, 2025 was doing what Earth does, generating the full range of its geological and meteorological capabilities, reminding its inhabitants that it is an active system that does not offer permanent safety, only the kind of provisional safety that comes from being adapted to the environment over millions of years of evolution. The crew of Artemis II was leaving that provisional safety behind for an environment to which no human being is adapted, for which no evolutionary preparation exists, toward which no rescue capability currently reaches, and in which the primary hazard was not wind or water or ground motion, but the electromagnetic output of a star in the peak phase of its 11-year activity cycle. That context, the comparison between the turbulence of a living planet and the deeper, quieter, more absolute hostility of the interplanetary space those 4 people were entering, is what the 12-hour convergence of April 1st illustrates, whatever its ultimate physical cause. The Earth was unsettled that night, but the crew was not heading somewhere more settled. They were heading somewhere where unsettled is simply the permanent condition, and the only question is how unsettled and for how long, and whether the sun decides to make it worse. Part 20. The Solar Seismic Question. There is a body of research that sits in uncomfortable territory. Uncomfortable not because the researchers are unreliable, but because the topic lives at the intersection of 2 fields with different cultures, different evidentiary standards, and a long history of disputed claims. The question is whether geomagnetic activity, the kind produced by CME impacts and solar wind fluctuations, has any measurable statistical association with seismic activity on Earth. It is the kind of question that makes mainstream geophysicists visibly uncomfortable at conferences, not because they think the question is stupid, but because the history of this particular line of inquiry is littered with overclaimed results, enthusiastically misrepresented findings, and a cottage industry of online speculation that has made serious researchers reluctant to engage with it publicly. The professional cost of being associated with a fringe result in a field with strong norms of empirical rigor is real, so the research that does exist on this topic tends to be cautious, heavily qualified, and published by people who understand they are operating in territory where the standard of proof required to be taken seriously is higher than average. The short answer from mainstream geophysics is probably not, or if there is an effect, it is extremely small and buried in noise. The Earth's crust is a system operating on timescales and at energy scales that dwarf anything a geomagnetic storm can plausibly deliver to it. Earthquakes are driven by the accumulation of stress along tectonic plate boundaries, a process that unfolds over decades to centuries as plates grind against each other, lock at fault surfaces, and gradually build elastic strain energy until a rupture propagates and releases it. The energy involved in a large earthquake is staggering. The magnitude 7.4 event in Indonesia released energy roughly equivalent to several hundred nuclear weapons. The idea that a perturbation in Earth's magnetic field, which during even a significant geomagnetic storm produces field variations of a fraction of a percent of the total field strength, could advance or trigger that kind of rupture on a timescale of hours is, from a straightforward energy budget perspective, very difficult to make work physically. And yet the research exists, not fringe blog posts, not YouTube speculation, peer-reviewed publications in legitimate scientific venues, including journals associated with the American Geophysical Union, the AGU, which is one of the most respected professional organizations in Earth and space science. These studies identify statistical correlations between periods of elevated geomagnetic activity and elevated rates of seismic events, typically in time windows of 1 to 3 days following significant geomagnetic disturbances. The correlations are not dramatic. They are not the kind of signal that leaps out of a dataset and announces itself. They are subtle statistical patterns that emerge from aggregated data across large numbers of events and long time series, the kind of signal that requires careful methodology to extract, and that is vulnerable to a range of analytical artifacts if the methodology is not carefully controlled. They are also not predictive in any operationally useful sense. Finding a statistical correlation between geomagnetic disturbances and elevated seismic rates in the following 1 to 3 days does not give you the ability to say that a specific CME arriving at Earth on a specific date will trigger a specific earthquake in a specific location. The correlation, if real, appears to operate at the level of population statistics, slightly elevated probability of seismic events globally in the days following geomagnetic disturbances, not at the level of individual event prediction. That distinction matters enormously, both scientifically and in terms of how the findings should be communicated to a public that is very good at hearing correlation and very bad at not hearing causation. The proposed physical mechanisms are where things get genuinely speculative, and it is worth spending a moment on them because the mechanism question is ultimately what determines whether the correlation, if real, represents a physical relationship or a statistical artifact. One class of proposed mechanisms involves piezoelectric effects, the property of certain crystalline rock types to generate electrical charges when subjected to mechanical stress, or conversely to develop mechanical stress when subjected to electrical fields. If geomagnetically induced currents in the crust produce electrical fields of sufficient magnitude in piezoelectric rock formations near active fault zones, they might, in principle, contribute an incremental stress to fault surfaces that are already near their failure threshold. The word might is doing significant work in that sentence. The magnitude of geomagnetically induced currents in crustal rock under the conditions produced by a G1 or G2 storm is orders of magnitude smaller than what would be required to produce mechanically significant piezoelectric stress. The mechanism is not impossible, it is implausible at the relevant scales, and no one has demonstrated it experimentally in conditions that resemble actual fault zone geology. Another class of proposed mechanisms involves ionospheric coupling, the idea that disturbances in the ionosphere produced by geomagnetic storms might propagate downward through the atmosphere and couple to surface systems in ways that influence crustal stress. This is a more physically subtle proposal, and it connects to a broader body of research on atmospheric-ionospheric lithospheric coupling that is itself an active and contested area of geoscience. The ionosphere clearly responds to solar activity, that is not in dispute. Whether those ionospheric responses couple downward to the solid Earth in ways that have seismological consequences is a question that remains genuinely open in the sense that it has not been convincingly answered in either direction. The coupling mechanisms proposed are physically plausible at the conceptual level. Whether they operate at the magnitudes required to be seismologically relevant is a different question, and the answer, honestly, is that we do not yet know. What makes this research thread worth taking seriously, even in its contested, inconclusive, methodologically disputed state, is not that it proves anything about the Indonesian earthquake on April 1st, 2025. It does not. The earthquake happened because a fault rupture occurred in one of the most seismically active regions on Earth, for reasons internal to the geological system, on a timeline set by decades of stress accumulation rather than hours of geomagnetic forcing. I'm not arguing otherwise, and I want that to be unambiguous. What makes the research worth taking seriously is what it points toward about the relationship between solar activity and Earth systems in general. The Sun is not a distant object whose influence on Earth is limited to the light and heat it provides. It is a dynamic, variable star whose electromagnetic output, particle emission, and magnetic field variations interact with Earth's atmosphere, ionosphere, magnetosphere, and potentially its geological systems in ways that we are still mapping. Every time researchers find a statistical signal, however small, however contested, however difficult to mechanistically explain, between solar activity and some Earth system response, it adds a data point to a picture of solar-terrestrial coupling that is more complex and more pervasive than the simplified version most people carry around. And that complexity is precisely what makes the situation of the Artemis II crew so clarifying when you hold it against the backdrop of this research. Whatever the Sun's influence on Earth systems might be, filtered through a magnetosphere that deflects the charged particles, an atmosphere that absorbs the electromagnetic radiation, thousands of kilometers of rock and water that attenuate any surface forcing, it arrives at Earth's surface already processed, already reduced, already mediated by layer upon layer of planetary protection that has been in place for billions of years. The geomagnetically induced currents that might, in the most optimistic reading of the contested literature, contribute a whisper of incremental stress to a fault zone, those currents are the tail end of a signal that started as a massive CME and was attenuated at every step of its journey from the Sun to the crust. The Artemis II crew has none of those layers. The CME that produced the geomagnetic storm that may or may not have contributed some infinitesimal forcing to a tectonic system that ruptured in Indonesia, that same CME, or the next one from region 4405 encountered by Orion in translunar space, is not attenuated. It is not filtered. It is not mediated by a magnetosphere or an atmosphere or thousands of kilometers of intervening material. It arrives at the capsule wall at full intensity, carrying its full complement of accelerated protons and energetic particles, and the only thing between that particle flux and the crew's biology is the capsule structure, the available shielding mass, and the shelter protocol. The question is not whether the Sun affects complex systems. It clearly, demonstrably, measurably does, from the ionosphere to the power grid to the statistical patterns in seismic catalogues that researchers are still arguing about in the pages of peer-reviewed journals. The Sun affects everything it touches, to varying degrees, through mechanisms that range from well understood to deeply contested. The question that is relevant to Artemis II, the question that nobody in the post-launch coverage was asking loudly enough, is how the Sun affects the most complex, most irreplaceable, most consequential system of all, the human body, when there is nothing in between. When the magnetosphere is behind you, the atmosphere is behind you, the planet is behind you, and the only thing between a solar particle event and your DNA is a few centimeters of aluminum and whatever you managed to stack around yourself in the back of the capsule before the proton flux peaked. That is the real question the solar seismic research thread points toward, even if it cannot answer it. The Sun is not a background condition. It is an active participant in this mission, and the crew of Artemis II right now is closer to that participation than any human being has been in 53 years. Part 21. The Human Layer. Step back for a moment from the data and the probabilities and the physics and consider the human picture of what this night represented. Because there is a version of this story that does not live in the SWPC forecasts or the proton flux measurements or the cumulative probability calculations, and it is in some ways the most important version. It is the version that is about 4 specific people, on a specific night, making a specific choice, and what that choice actually means when you hold it up against everything else that was happening on Earth at the same moment. While the earthquake warnings were propagating across Indonesian coastal communities, while emergency broadcast systems were interrupting regular programming, and coastal residents were making the calculation of how quickly they could reach high ground, 4 people were strapping into a capsule. While tornado sirens were sounding across the American Midwest, while families were sheltering in basements and interior hallways with mattresses pulled over their heads and phones displaying emergency alerts in red, 4 people were running through their pre-launch checklist. While the geomagnetic storm was inducing currents in power grid infrastructure across the high latitudes of North America and Europe, while grid operators were quietly implementing disturbance protocols and hoping the KP index did not climb another level, 4 people were waiting for a rocket to light beneath them, in full knowledge of the solar environment that had produced the storm, in full knowledge of what they were about to enter. They chose to leave, in the middle of all of it, with all of it visible to them, because these are people whose professional lives are built around monitoring exactly the kind of conditions that were active on April 1st, 2025. They did not leave in ignorance. They left with their eyes fully open, which is a categorically different kind of departure. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. I want to say their names again, because one of the things that large-scale coverage of historic events does, almost inevitably, is convert specific people into representative figures. They become symbols of the program, icons of the mission, faces on the poster. And that is not wrong. They are those things, and those things matter. But they are also something more particular and more fragile than symbols. They are human beings with families who watched the launch from the ground and felt something that no broadcast camera can fully capture. They are people who have spent years, in some cases the better part of a decade, preparing for a mission window that lasted 8 days. They are individuals who carry in their minds a precise and detailed understanding of the risk environment they were entering, because that understanding is part of their professional preparation, and you cannot prepare adequately for something you are not willing to look at directly. They know about Region 4405, not as a news item, not as a detail they encountered while browsing headlines on the morning of the launch, but as a classified, monitored, actively tracked threat that was part of their mission briefings and their risk assessments and the space weather support provided to the program by NOAA and NASA's own space weather team. They know about the cumulative probability of an X-class flare during their transit window, because that probability was calculated by people whose job it is to calculate it and communicated to people whose job it is to act on it. They know about the August 1972 solar particle event, because it is one of the foundational case studies in the radiation risk literature for crewed deep space missions, the event that established the outer boundary of what the Sun is capable of delivering to unshielded humans in the inner solar system, the event that missed the Apollo crews by timing alone, the event that every subsequent generation of mission planners has used as the anchor point for their worst-case scenario modelling. They know about the 30-minute problem, the window between flare detection and meaningful proton arrival, the window inside which the shelter protocol must be executed, the window that is wide enough to be workable and narrow enough to be uncomfortable. They know about the limits of the improvised shielding available inside Orion, what it can attenuate and what it cannot, where the protection ends and the residual exposure begins. They have read the same papers, run the same drills, sat through the same briefings. The risk is not abstract to them, it is operational. It is the thing they prepared for specifically and in detail, because preparation is the only honest response to a risk you cannot eliminate. And then they got in the capsule anyway. There is a kind of courage in that decision that I think deserves more precise language than the word brave typically provides, because brave has become so broadly applied that it has lost some of its resolution. What these 4 people demonstrated is something more specific. It is the courage that comes not from the absence of fear or the minimization of risk, but from a clear-eyed assessment of the full picture, the known risks and the unknown risks, the tail events and the margins, the August 1972 scenarios and the probability distributions and the 30-minute windows, followed by a deliberate conclusion that the thing being asked of them is worth the exposure. Not that it is safe, not that the risks are acceptable in the sense of being small, that it is worth it. Worth the cumulative probability, worth the 8 days in an unshielded environment during an active solar maximum, worth the margin between the designed performance of the shelter protocol and the tail of the SPE intensity distribution. Worth whatever the Sun decides to do in the next 8 days. That is not a calculation, that is an affirmation. And it is a categorically different thing from the bravery we usually celebrate, which tends to be reactive, the courage that emerges in a moment of crisis when someone acts quickly and decisively under pressure. What these 4 people demonstrated was prospective courage, the willingness to walk into a situation with full knowledge of its worst-case scenarios and choose to walk in anyway, before the crisis, before the adrenaline, in the cold light of complete information. That is rarer and in some ways harder than the reactive kind, because there is no emergency to metabolize the fear. There is only the knowledge and the choice and the walk to the capsule. And yet, as this planet was generating its own catalogue of turbulence that night, the earthquake, the tornadoes, the flooding, the geomagnetic disturbances, the crew's situation illustrates something about the hierarchy of human vulnerability that the news coverage somewhat flattened in its celebration. Not intentionally, not through any failure of journalistic integrity, but because the celebration was real and deserved, and because the full picture of what those 4 people were actually entering is genuinely difficult to hold in the mind simultaneously with the image of a rocket climbing beautifully through a Florida evening sky. The brain wants to hold one image. The truth requires holding 2. The tornado warnings were serious. The people sheltering in basements across the Midwest were in genuine danger, and some of them were hurt and their experience was real. The earthquake was serious. The communities on Indonesian coastlines watching tsunami waves approach were facing something terrifying and immediate, and their fear was entirely proportionate to the situation. None of that is minimized by anything I am about to say. The danger on Earth that night was real, but the people facing that danger were on a planet. They were inside an atmosphere that limits radiation exposure and moderates temperature extremes, and provides the air that keeps them alive without any technological assistance. They were inside a magnetic field that was, even in its storm-perturbed state, deflecting the solar wind that the Artemis II crew would shortly be encountering without any deflection at all. They had access within hours to emergency services with equipment and training and communication infrastructure, and the accumulated knowledge of a civilization that has been developing better ways to survive its own planet's violence for as long as civilization has existed. They were embedded in a support network that spans the species, meteorologists and seismologists, and emergency managers and search and rescue teams and hospitals, and the entire distributed infrastructure of mutual aid that human societies have built precisely because the planet they live on is capable of nights like April 1st, 2025. The 4 people now travelling toward the moon had a capsule. They had a shelter protocol, they had HERA sensors and personal dosimeters, and a 30-minute warning window. They had each other. And they had 8 days of exposure to whatever the sun chose to do, in an environment where no rescue operation currently exists, where no emergency service can reach, where the distance between them and the nearest hospital was measured in hundreds of thousands of miles and growing larger with every passing minute. The contrast is not meant to diminish anything that happened on Earth that night. It is meant to accurately locate where the most absolute, unmitigated, structurally irreducible human risk was concentrated at the moment the launch clocks ran to 0. It was not in the basement shelters of the Midwest. It was not on the coastlines of Indonesia. It was concentrated in a capsule, crossing the Van Allen belts, with an active solar region aimed at its trajectory, and a sun that was, by any contemporary measure, not done talking. 4 people chose that, knowingly, deliberately, on behalf of a species that needed someone to go and found, as it has found before, that there were people willing to be that someone. The least we can do, in return for that willingness, is understand fully what they walked into, not the version that fits inside a celebration, the whole version, the one that includes Region 4405 and the cumulative probability and the 30-minute window and the 8 days and the sun that is still active as you watch this. That version, because that is the one that is true. Part 22. The first real test of deep space risk. What Artemis II actually is, underneath the framing of historic mission and return to the moon and giant leap, underneath the broadcast coverage and the crowd noise and the slow-motion footage of the engines igniting, is a test. A live, crude test of whether the systems we have built over the past 50 years of thinking about this problem are actually adequate for the real-world conditions of crude, deep space flight during solar maximum. Not adequate in the sense of passing a review board, not adequate in the sense of satisfying an engineering checklist, adequate in the sense that 4 human beings can transit the interplanetary radiation environment during an active phase of the solar cycle and return to Earth with their biology intact and their dose records within mission-acceptable parameters. That is the test, and it is being conducted right now in real time with no opportunity for a dry run. This is not a criticism of the program. Tests are how knowledge advances. Tests are how you find out whether the models that look correct on paper hold up when they encounter the thing they were built to model. The history of aerospace is, in a meaningful sense, the history of tests, some of which returned the data that confirmed the models, and some of which returned data that revealed, at significant cost, that the models needed revision. Artemis II is a test in that tradition, and the tradition is honourable. But it is worth being precise about what kind of test it is, because the framing of historic mission and return to the moon tends to suggest a triumphal narrative, a thing we're doing because we already know we can, rather than an investigative one, which is closer to the truth. Everything we know about radiation risk in translunar space comes from sources that are either old, indirect, or both. The Apollo program gives us the most direct data: 12 people who transited the Van Allen belts and spent time in the cislunar and translunar environment across 6 successful landing missions and several additional missions that did not land. Their personal dosimeters recorded cumulative doses. Their medical records have been followed for decades, and researchers have attempted to extract from those records any signal of radiation-related health effects that might be attributable to their missions. The results are suggestive in some dimensions and inconclusive in others, partly because the sample size is small, 12 people, and partly because the Apollo missions occurred at varying points in the solar cycle, with varying levels of solar activity, and the individual dose records vary accordingly. Apollo 16 and 17 flew during a period of elevated solar activity. The August 1972 event occurred between them. The data from that era is real and valuable, and it has been the foundation of everything that followed. It is also 50 years old, collected with instrumentation that, while adequate for its time, cannot be directly compared to modern sensors without significant uncertainty in the calibration. Beyond Apollo, the radiation knowledge base for translunar space comes from uncrewed probes, spacecraft that have carried radiation instruments through the translunar environment and beyond, providing continuous measurements of the galactic cosmic ray background and solar particle event intensities at various points in the solar system. The data from these instruments is excellent. It has allowed physicists to build detailed models of the interplanetary radiation environment and how it varies with solar activity, heliocentric distance, and the geometry of the heliospheric magnetic field. But uncrewed instruments measure physical quantities. They do not measure biological response. They tell you how many particles of what energy arrive at a given location. They do not tell you what those particles do to a human body over 8 days of continuous exposure, because the relationship between particle flux and biological dose, and between biological dose and health outcome, involves layers of complexity, tissue type, dose rate, particle species, individual variation in radiosensitivity that cannot be fully captured by a physical instrument alone. Animal studies have contributed to the biological side of the picture. Rodents and other organisms have been exposed to simulated space radiation environments in ground-based facilities, particle accelerators that can produce beams of heavy ions at energies approximating the galactic cosmic ray spectrum. The results from these studies have been informative and in some dimensions concerning. Cognitive effects, cardiovascular effects, increased cancer risk. These have been observed in animal models at dose levels relevant to deep space missions. The translation from rodent biology to human biology is never straightforward, and the researchers who conduct these studies are careful about overclaiming the human relevance of their findings. But the animal data is the best biological evidence available for the effects of the specific radiation environment of deep space, and it has informed the risk models that underpin the mission safety case. Analog environments, high-altitude aviation, the International Space Station, provide human data but in environments that differ from translunar space in critical ways. High-altitude aviators receive elevated cosmic ray exposure compared to people at sea level, but they are still inside Earth's magnetosphere, still partially shielded, still receiving a radiation environment that is fundamentally different in character from the unshielded interplanetary environment. ISS astronauts receive substantially higher doses than people on Earth, and their health outcomes have been studied extensively. But the ISS orbits at approximately 400 kilometers altitude, well inside the magnetosphere, and the radiation environment there, while elevated, is not representative of what exists beyond the Van Allen belts. The shielding contribution of Earth's magnetic field at ISS altitude is significant. Remove it, and the environment changes in ways that the ISS data cannot fully capture. Into all of this uncertainty, the 50-year-old Apollo data, the uncrewed probe measurements, the animal studies, the imperfect analogues, Artemis II is about to introduce something genuinely new. Real-time, crude human radiation measurements in the translunar environment during solar maximum with modern instrumentation correlatable against the most comprehensive concurrent space weather observational network ever assembled. The HERA sensors inside Orion will measure the radiation environment continuously throughout the mission. Personal dosimeters worn by each crew member will record individual dose accumulation. The data will be downlinked to mission control, analysed in real time, and eventually, after the mission concludes and the crew undergoes post-flight medical evaluation, integrated into the most complete picture of human deep space radiation exposure that has existed since the Apollo program ended. That dataset will either validate the risk models that underpin the entire Artemis program safety case, or it will reveal gaps. And the nature of those gaps matters enormously for everything that follows. If the measured doses are within the predicted ranges, if the shelter protocol performs as modelled during any solar particle events that occur, if the crew returns with dose records that fall within the pre-mission projections, then the risk architecture for Artemis III, the first crewed lunar landing attempt, will rest on a foundation of confirmed modern human data rather than 50-year-old measurements and model extrapolations. That is not a small thing. That is the difference between a safety case that is theoretically justified and one that is empirically grounded. If the data reveals discrepancies, if the measured doses are higher than predicted, if the shelter protocol proves less effective than modelled, if a solar particle event produces a crew response that identifies gaps in the warning and shelter system, then those discrepancies become engineering requirements for Artemis III. They become the inputs to design changes, protocol revisions, shielding improvements, whatever the data indicates is necessary before a crew spends substantially longer periods on the lunar surface, where the radiation environment is comparable to translunar space, and the mission duration is measured not in days but in weeks. The lunar surface offers no magnetospheric protection. It offers minimal atmospheric shielding. A crew member conducting an EVAS-A on the lunar surface during a solar particle event is in a more exposed position than the Artemis II crew inside Orion, and the suit shielding available for lunar EVAs is significantly less than the capsule shielding available for in-flight shelter. Getting the radiation risk model right before that scenario is attempted is not a bureaucratic priority. It is a human safety priority, and the consequences extend further still. Beyond Artemis III, beyond the lunar program, to the missions that the next generation of mission planners is already beginning to think about. Crewed missions to Mars, to the asteroid belt, to destinations in the solar system where Earth's magnetic protection is not just reduced, but effectively irrelevant at the distances involved. The radiation environment on a Mars transit is substantially more demanding than the translunar environment. The mission duration is measured in months, not days. The solar particle event probability over a Mars mission window is not 57%, it approaches certainty. Whatever we learn from Artemis II about the performance of crewed deep space radiation management systems under real solar maximum conditions will be foundational knowledge for the people who have to design the systems that keep a Mars crew alive through events that are not possible to avoid, only to manage. This is not a mission that ends when Orion splashes down. Its consequences extend forward through every crewed deep space mission that NASA and other space agencies and eventually commercial operators will attempt in the coming decades. The radiation risk management architecture for the entire era of human deep space exploration is being validated in real time during these 8 days in April of 2025. The Sun knows nothing of this. It does not know it is being studied. It does not know that the data its behaviour generates over the next 8 days will be passed by researchers for years, fed into models that will govern decisions about human lives on missions that have not yet been named. It simply continues being a star, 4.6 billion years old, 109 times the diameter of Earth, producing energy at a rate that makes every human power source look like a birthday candle, cycling through its 11-year activity pattern with the indifference of something that has been doing this since before the Earth existed and will continue doing it long after the Earth is gone. And inside a capsule crossing the Van Allen belts on its way to the Moon, 4 human beings are generating the data that will tell us whether we have learned enough about that star to safely send more people into its influence. The answer is coming. We're about to find out what it is. Part 23. The Fragility of the System. There is something clarifying about looking at the full stack of systems that have to function correctly for this mission to go well, because the list is long and each element is necessary, and the act of laying them out in sequence one after another, each depending on the one before it, produces a picture that the summary descriptions of mission safety do not quite capture. It is the difference between being told that a bridge is well engineered and actually walking across it while looking down at the water. The engineering is the same in both cases, the understanding is different. Start at the beginning of the chain. The Space Weather Prediction Center's forecast models have to correctly characterize the evolution of active region 4405, its magnetic complexity, its flare probability, the trajectory and speed of any CMEs it produces, and do so with sufficient accuracy and sufficient lead time to provide actionable information to mission control. This is not a simple modelling problem. Solar active regions are dynamic systems whose behaviour emerges from magneto-hydrodynamic processes that operate across a range of spatial scales, from the global structure of the solar magnetic field down to the fine structure of individual sunspot penumbra. The models that predict flare probability are statistical, built on historical associations between magnetic classification and observed flare rates. They are well validated against historical data, but they are probabilistic, not deterministic. They tell you the likelihood of an event, not when it will occur or what its precise characteristics will be. And for the tail events, the extreme eruptions that fall at the high end of the intensity distribution, the historical dataset is thin, because extreme events are by definition rare, and rare events produce sparse training data for statistical models. The SWPC models are the best available. They are not perfect, and for this mission, perfect is what would be most useful. The forecast models are only the first link. The next link is the observational infrastructure that feeds them, and that the mission depends on independently for real-time solar wind monitoring. A CE, the Advanced Composition Explorer, has been operating at the Lagrange 1 point since 1997. It is 28 years old. It was designed for a mission life of 3 to 5 years and has operated for more than 5 times its design lifetime through a combination of engineering conservatism and careful fuel management. Its instruments continue to function, but they are aging hardware operating well beyond their intended lifespan in the radiation environment of the L1 point, which is itself not a gentle place for sensitive electronics. DSCOVER, the Deep Space Climate Observatory, provides complementary solar wind monitoring and serves as a backup for ACE's real-time data stream. Both spacecraft have to remain operational and transmitting throughout the Artemis II transit window. A failure of either, particularly ACE, would degrade the real-time solar wind monitoring capability at the moment when that capability is most needed. The probability of such a failure during any specific 8-day window is low. It is not zero, and the spacecraft are old. Assuming the monitoring infrastructure functions and the forecast models produce an accurate characterization of the solar wind environment, and any incoming SPE, the next link is the alert chain. The sequence by which a solar event detection at NOAA propagates through the institutional structure to mission control, and from mission control to the crew, has to function within the time window available, which, as we have already established, can be as short as 15 minutes for the fastest high-energy particle arrivals from a major flare. This chain involves automated systems, human decision-makers, communication infrastructure, and the crew's own monitoring and response capability. Each handoff in the chain introduces latency. Automated detection systems have processing delays. Human reviewers require time to assess data quality and confirm the event characterization before issuing alerts. Communication between NOAA and Mission Control, and between Mission Control and Orion, involves transmission delays that are small at lunar distances but not zero, and at greater distances would become significant. The chain has been designed to minimize these latencies. It has been exercised in simulations. It has not been exercised in the actual conditions of a major SPE during a crewed translunar mission, because no such mission has occurred in the modern era. Inside the capsule, the HERA sensors, the hybrid electronic radiation assessor, have to accurately measure the dose rate environment in real time, distinguishing between the galactic cosmic ray background and any elevated SPE flux, providing the crew and mission control with data that is accurate enough to inform shelter decisions and duration assessments. Radiation detectors in space are robust instruments with well-characterized response functions, and Hera represents a significant improvement over the dosimetry available to the Apollo crews. But radiation instruments can be saturated by extremely high particle fluxes. The very fluxes associated with the most extreme SPEs are also the ones most likely to challenge the dynamic range of the detection systems. This is a known engineering consideration, and the Hera design accounts for it. Whether the accounting is adequate for the tail of the SPE intensity distribution is a question that, by definition, can only be answered by encountering an event in that tail. When the alert is received and the crew moves to shelter, the effectiveness of that shelter depends on their positioning relative to the available shielding mass, the equipment, water containers, food packages, and structural elements that can be interposed between the crew and the incoming radiation. The attenuation achieved depends on the mass and composition of the shielding, the geometry of the crew positioning, and the energy spectrum of the incoming particles. Lower energy protons are more effectively shielded than higher energy ones. The most extreme SPEs tend to produce harder energy spectra, more high energy protons, which are also the ones that penetrate shielding most effectively and produce the most secondary radiation in the shielding material itself. The shelter protocol was designed around the expected SPE characteristics for events within the design case intensity range. For events at the tail of the distribution, the geometry and mass of the improvised shelter inside Orion may produce less attenuation than the design case assumes. Not no attenuation, some attenuation, and meaningful attenuation. But the margin between the design case performance and the actual performance under extreme conditions is not precisely known, because it has not been empirically measured. Throughout all of this, the forecasting, the monitoring, the alerting, the sheltering, the Orion capsule itself has to continue functioning nominally. Radiation affects electronics. High-energy particles cause single-event upsets in digital systems, bit flips, logic errors, memory corruption, and insufficient flux can cause more serious damage to sensitive components. Orion's electronics are radiation-hardened, designed to tolerate the deep space environment. But radiation hardening is specified to a design tolerance, and extreme SPEs produce particle fluxes that can approach or exceed the design tolerance of hardened electronics in the most severe cases. A single event upset in a critical avionics system at the wrong moment during an SPE when the crew is in shelter and mission control is managing multiple simultaneous anomalies is a scenario that the design tries to prevent and cannot guarantee to eliminate, and mission control itself is a link in the chain. The human being sitting at the consoles in Houston during a significant solar event, receiving data from SWPC and from Orion simultaneously, making real-time decisions about shelter duration and abort considerations and systems management, are operating under time pressure in a scenario that has been simulated but never lived. Simulation is excellent preparation. It is not the same as the actual event. The cognitive load of managing a significant SPE during a crewed translunar mission, with incomplete data, compressed timelines, and consequences that are not simulated, is a human performance challenge that no amount of training can fully replicate in advance. Every link in this chain is well engineered. Every link has been tested and validated to the extent that testing and validation are possible for a mission that has never flown before in these specific conditions. The people who designed these systems are not naive, and they are not cavalier. They have done everything that the current state of knowledge and technology permits to make each link as strong as possible. That is true, and it matters, and it deserves to be said clearly. But a chain's strength is determined by its weakest link under actual conditions, not by the average strength of its links under test conditions. And the actual conditions of an extreme solar particle event arriving faster than the median model prediction, with an intensity at the tail of the historical distribution, with a harder energy spectrum than the design case assumes, while the crew is in a configuration inside the capsule that is not the optimal shelter position, while one of the monitoring spacecraft is experiencing an age-related data dropout, while mission control is working through the latency of an alert chain that is performing at its design limit. Those conditions have never been encountered by this specific chain of systems operating simultaneously. Because this specific chain of systems has never operated simultaneously in these conditions before. That is what it means to be the first. The margin is not zero. NASA does not design missions with zero margin, and the margins built into this system are real and meaningful, and the product of serious engineering effort. but the margin is finite, and the solar environment during this mission has already demonstrated before the crew has even crossed the Van Allen belts that it is capable of placing demands on the system at the high end of the operational range. The G1 storm on launch night was not a maximum demand event. It was a reminder that the system is active, that the demands are real, and that the chain will be asked to perform. A single significant solar event during the transit window would stress every link in that chain simultaneously. The forecast models would have to characterize a fast-moving complex event accurately and quickly. The monitoring spacecraft would have to be functioning and transmitting. The alert chain would have to propagate the warning within the available time window. The crew would have to execute the shelter protocol correctly and completely. The HERA sensors would have to provide accurate real-time dose data. The capsule electronics would have to tolerate the particle environment. Mission control would have to make correct decisions under pressure with incomplete information. Not necessarily to the breaking point. The chain might hold at every link. Probably it would. The engineering is good, the training is thorough, the monitoring is comprehensive, and the probability that all links hold under even significant demand is substantially higher than the probability that any single link fails. But the stressing would be real, and the outcome would depend on details, the precise intensity of the event, the exact timing of the warning, the specific configuration of the crew at the moment of peak flux, the performance of aging hardware under conditions it was not designed to encounter, that no model has fully characterized, because no model can fully characterize what it has never been asked to predict for a situation that has never occurred. That is the chain. It is strong. It is finite. And right now, it is being asked to hold. Part 24. Final question. Right now, as you watch this, the Orion capsule is still in space. The TLI burn either has fired or is about to fire. If it has fired, the crew is already on a trajectory beyond the Van Allen belts, already in the radiation environment that has been the subject of this entire conversation. Active region 4405 is still on the solar disk. The Sun's 11-year cycle is still near its peak. The daily probability of an X-class flare from that single region is still approximately 10%. The question that this mission poses to everyone watching it is not really a technical question. The technical questions have been answered as well as they can be answered with the knowledge and tools available to us in 2025. The question is philosophical, and it is the same question that every era of human exploration has eventually forced its civilization to confront. How much risk is acceptable in exchange for the things that only risk can purchase? The Apollo program asked that question, and answered it with 12 men who walked on the moon, and 2 astronauts who nearly died getting there, and 3 astronauts who died on the launch pad before the program had even properly begun. The answer was, enough risk to accept those outcomes in exchange for what was gained. We still do not all agree on whether that was the right answer. Artemis II is asking the same question in a new context, with new technology, and with a solar environment that is adding its own unsolicited commentary to the proceedings. 4 human beings crossed the threshold of our magnetic protection with the knowledge of what they were crossing into, and the conviction that the crossing was worth making. Whether the Sun agrees with that assessment is something we will find out over the next 8 days. The most extraordinary thing about space exploration, the thing that never fully makes it into the broadcast coverage, no matter how much airtime the launches receive, is that it is a negotiation, not between humans and machines, not between agencies and budgets, not between competing national programs. It is a negotiation between human ambition and the indifference of the universe. Every mission is a bid, every launch is an offer, and the universe replies on its own schedule, in its own language, without regard for the celebrations happening 93 million miles away. The Sun does not know that 4 people are out there. It does not know about the shelter protocol, or the HERA sensors, or the cumulative probability models, or the 53 years of waiting that preceded this moment. It is simply a star, 933,000 miles in diameter, in the middle of its peak activity phase, with a magnetically complex active region aimed at the inner solar system. And the crew of Artemis II is flying directly into its light. Whether the universe sends back a favourable reply is a question that only the next 8 days can answer. Stay with us.